and then it's all right. Don't let's see. Yeah, there. If you click there, I think. Let's see. Camera is screen. Maybe the screen go under the screen. Widescreen show taskbar. Nope. Okay, that's not it. It's clean. Camera help. Okay, don't worry. I think we'll just go with this mode, and then that's it. You know, that's not a problem.
Okay.
Let's just go with this mode. Bottom left, it says, okay, maybe the bottom, the bottom left is maybe everybody wants to like, yeah, display settings. The problem is that display settings, you cannot see the one on the top. No, that's the laser pointer, that's fine. And that button in there, the display settings, if you click there, and you click that display settings, that is, that's the different one. No, sorry, that's the wrong one. We shouldn't have done that. Okay, that's good. Just leave it like that. All right. Well, let's thank everybody. Sorry for we have some issues from the other side that we're trying to figure it out. We're going to be using this display setting today because of other technical issues. Welcome once again to the online SPICE and SPIN+X seminar series that I organize here in collaboration with the SPIN+X Collaborative Research Center in Casus Latin and Mainz. And as I mentioned, in all the talks, we typically do this at 3 o'clock, but not every week. Just please see the schedule and sign up, of course, to receive the emails on Monday and Wednesday to let you know about the upcoming seminars of that week. Today is a pleasure to have Ron Naaman with us from the Weizmann Institute of Science in Israel. And he has had many contributions to our field of physics and chemistry. He's a fellow of the American Physical Society, fellow of the Royal Society of Chemistry, member of the Academy of Europeum, and recipient of the Chiral Medal and the Gold Medal of the Israeli Chemical Society, plus among many other awards. But one of the things that really characterizes is the discovery of this experimental discovery of this Chiral-induced spin selectivity that has kept us very busy for quite a while. It's now becoming quite important and has been important now for a bit. And then some of the things we're figuring it out, some of the things still remain a puzzle. And with that, I'd like to give you the floor. Please go ahead and start your talk. Yeah.
Okay. Thank you very much. And it's a pleasure to be with you all. And I apologize in advance if there would be sirens here. I will ignore them, but we do have sirens because of this war going on in our area. Okay, I dedicate my talk to my really close friend and collaborator, Dave Waldeck, that died just a week ago. And Dave was a special person and amazing scientist. And I think I personally will miss him always. And the community, the CISS community, will definitely miss him, as well as the department in Pittsburgh and so on. He was really a special person. Okay, we will start with the chirality. I know that you all know what is chirality, but there is an interesting question. We all know that in nature we have homochirality, so most important molecules in nature, like proteins, amino acids, of course, sugars, DNA, etc., they are chiral, and they come in one enantiomer. And the question one should ask, perhaps, is why chirality is kept so persistently through evolution? Because you should realize that keeping homochirality means reducing entropy, and therefore it means that one has to pay price in energy. And the question, why is nature willing to pay this price? What advantage nature has from having homochirality? And I think usually it was assumed that chirality is mainly a structural phenomenon. I want to show you that It is much more than this. And the effect that I'm going to discuss is, of course, the chirality induced spin selectivity effect, CISS. And the CISS says basically that when electron moves within a chiral potential, the motion of the electron is spin dependent. Which spin is preferred depends on the endedness of the system and direction of the electron motion, namely electron moving in a system from left to right will have one spin, going backwards will have the opposite spin in laboratory frame. But actually, to make it clearer, for one enantiomer, the spin will be always aligned parallel to the velocity. For the other enantiomer, it will be aligned always anti-parallel to the electron velocity. So, okay, how can we vision the CISS effect? And I apologize, but I have a very simple model. And as you will see along my talk, despite the model being so simple, it is very valid for understanding the CISS effect. So the effect is the effect of frisbee. Think about a frisbee that we throw rotating towards the right wall. In this case, if the frisbee, sorry, that's what I mentioned. It's a okay. So if I throw the frisbee to the right wall, if the frisbee rotates clockwise, it will scatter forwards. If it rotates counterclockwise, it will rotate backwards. And sorry, and of course, the opposite will happen if I throw it to the left wall. So what it means, what this effect means. So we need for this effect, of course, angular momentum, because all the effect results from coupling of linear momentum with angular momentum. Secondly, we need to break symmetry, like the right wall and left wall. You can think about right-handed molecule and left-handed molecule. And the third thing we need is friction, namely a way to couple the two momenta. And in macroscopic system, it's spin-orbit coupling. It's a friction. However, in a microscopic system, it's spin-orbit coupling plus dissipation. So as you will see, this really describes the CISS effect. Now, before going more in details into the CISS effect, I want to say a few words about spin. You know, in chemistry and in physics, we assume that spin is important only when we have either paramagnetic or ferromagnetic systems, namely open shell systems. However, it's even more interesting that in molecules, even if you have unpaired electron, typically it is assumed that this unpaired electron is only weakly coupled to the molecular frame. That's the reason we can do EPR spectroscopy. When we apply magnetic field, we align the spin, and the molecule can tumble, but still the spin is aligned relative in the laboratory frame by the magnetic field. So because of this, typically in chemistry, it was assumed that controlling spin in bimolecular reaction, for example, is not going to affect the reaction. So what the CISS tells us that, first of all, even chiral molecules that are singlet, the spin plays an important role. And interestingly, the spin is strongly coupled to the molecular frame. So let's think about electron moving through helical potential. Now you should appreciate that even if the secondary structure of the system is not helical, if you have even a single carbon atom with 4 different groups attached to it, then if we follow the electrostatic the electronegativity, let's say, of these atoms, we get helical electrostatic potential. So helical electrostatic potential does not require secondary structure of the molecule. In any chiral molecule, we have helical, at least in part of the potential is helical. So if we look on this, what it's obvious that electron going through such helical potential must exchange momentum with the system. It cannot go through without colliding with the system. That's very different from what we know in regular conduction in condensed matter physics or in molecules. Typically, when we speak about conduction through molecules, we speak about electron going in straight line. Even if the molecule is not linear, people assume linear transmission. And if you assume linear transmission, then obviously any interaction of the electron with the environment will destroy the transmission. However, in helical molecules, we need the interaction with the environment, with the molecule. So what can exchange momentum with the passing electron? In solid, when we have a band structure, then the electron can exchange momentum with electrons in the band because they can change momentum easily without, it doesn't require much energy. However, if we have insulators, like molecules, then the electrons are localized. Then, of course, the electrons by themselves cannot take momentum because then it will require a lot of energy to change momentum of a localized electron. The only candidate then to take momentum is these vibrations, and mainly we are speaking about vibrations that have angular momentum, which we call chiral vibrations. So in the sense, when we came out with the CISS effect, it surprised both chemists and physicists. And first of all, chemists, as I mentioned before, spins were typically ignored for closed-shell systems. The second surprise was that typically hydrocarbon, that are most of the organic molecules, a very small spin-orbit coupling. The CISS effect was observed at room temperature. How come that the system with very small spin-orbit coupling shows spin-dependent properties? And especially what was amazing, how one gets such a large spin polarization at room temperature. And sometimes the spin polarization exceeds the spin polarization of the ferromagnet from which electrons were ejected. So as you will see, we have very high spin polarization here at room temperature, something which is completely counterintuitive for people working on spins. So let's take a simple experiment, and that I think demonstrate the properties of the CISS. Let's see if, okay, now I have it. So basically we have here a ferromagnet substrate on top of which we adsorbed chiral molecules. We come with a conducting tip of an AFM and measure the current between the ferromagnet and the tip when the ferromagnet is magnetized in either with the North Pole pointing up or the North Pole pointing down. If we see different in the current versus voltage curve, it means that we have spin selective transmission. So what we get, that's a typical result here. You see that we get two curves. In this case, the molecules are double-strand DNA, 20 base pair, and you see very different curves for the two spins. And what is really amazing when we look at the half-logs graph, we see that there is different threshold for injecting one spin and the other spin into the molecule. And the different threshold, the difference between the threshold is on the order of 100 of milli electron volt. It's a huge difference in the injection barrier into the Chiral molecule. And this is basically twice the effective spin-orbit coupling in the system. So we see here that we have spin-orbit coupling, effective spin-orbit coupling. In a moment, we'll discuss what it means, effective spin-orbit coupling. Effective spin-orbit coupling, which is several orders of magnitude larger than what you expect from hydrocarbon. Here you see the length dependent of the spin polarization, and this is for double-strand DNA, and this is for oligopeptides. Now, interesting to see that despite the fact that the values look similar, you see here it's about 60+%, here it's 45 and so, but here the length of the DNA is 12 nanometer, while the length of the oligopeptides, alpha helix oligopeptide, is less than 3 nanometer. So per nanometer, the alpha helix is more efficient spin filter, if you wish, than the double-strand DNA. And we can now look for the dependence of the current for each spin as function of the length. So you realize for one spin, which we call the preferred spin, we see that the current decays very slowly as function of the length, while for the other spin, it decays very fast. The reason it decays very slowly is because the spin is coupled to the linear momentum, and if the electron has to backscatter, it has to flip spin. Flipping spin is not highly probable. As a result, we get very long range electron transfer. For the wrong spin, of course, backscattering is efficient, and therefore it decays very fast. So it's really interesting to note that while for electron moving in straight line, the vibration and the interaction with the area, with the system actually cause the depletion of the current. In the case of CISS, the electron that did interact with the environment, those are the electrons that came through. So in a sense, is that we have a complementary population. Think about it. In the case of the Chiral molecules, we see the electron that we don't see in the linear transmission. It's really a basic difference that confused many people trying to model the CISS effect. They didn't realize that in the CISS case, you have to take into account the interaction with the molecule. Now, what the role of phonons for this is another study in which we basically put Chiral molecules between a gold substrate. On top, there is a thin magnesium oxide layer to block pinholes, and then a nickel layer that can be magnetized up and down. And we measure this current flowing with magnet one direction and other direction. Basically, it's the magnetoresistance. And what we get here is spin polarization. And to our surprise, we see that the spin polarization actually increases with the temperature. And here it's the Arrhenius plot. So you see we start at 5K, we have some value. It is reduced up to 50K, but at 50K we start to populate vibrations that are relevant to this CISS effect, namely vibration that are chiral. And then we get very fast increase in the spin polarization. And theory by Jonas Franson actually simulate very nicely the effect. So what we conclude from this, that in this specific case, vibrations are important. I want to make a word about, of a comment here. As I mentioned, vibration are important in the case that there are no delocalized electrons. If there are delocalized electrons in the system, then of course electron scattering will be more efficient than electron phonon scattering, and then we are not going to see temperature dependent. So the temperature dependent here, it's not that in CISS always you see a increasing of the effect with temperature. It depends on the molecular system. Now we go to another property which is quite interesting. It's how to relate CISS to optical activity. For this work, we joined forces with a group of Bert Meyer in Eindhoven, and Bert synthesizes these molecules here, the porphyrin, and the porphyrin has here R group, and this R group can be either chiral or non-chiral. If it's chiral, it assembles to wires that are chiral. If it's not chiral, then it's the wires are randomly arranged. And now the question is, can we see spin selectivity first? So what you see here, the wires are lying on the surface. We come with the tip of the AFM and we measure, and please realize that we measure in this case the current going perpendicular to the long axis of the wire. And this is the height of the wire. So you see the thickness of the wire. So you see it's between 15 to 20 nanometer. Namely, these wires are not made from single molecules, but they are made from a bundle of molecules, and therefore they are quite thick. And now we measure the spin polarization as we did before for different R. These are all the R's here are chiral, and you see that indeed, depending on the group, we get different spin polarization. And what is interesting, you see here, we can get up to about 90% spin polarization in this case. Huge effect. But what is more interesting is that when these wires are made, one can use a technique known by people working on supramolecular, chiral supramolecular structure. It's called sergeant and soldier. What it means that one can take achiral molecules and assemble the wires with by doping some amount of chiral molecules. So the achiral molecules are the surgeon, the chiral molecule, are the soldiers, the chiral molecules are the surgeon, and as a result, what you see here is the CD spectrum, the intensity of the first peak in the CD spectrum, the lower energy peak in the CD spectrum. And what you see when we increase the fraction of the chiral molecules, in the beginning, there is a linear dependence of the CD, circular dichroism spectrum intensity on the amount of chiral molecules, but then there is an amplification. This effect is well known in the community of chiral supramolecular structure, namely the chiral molecule dictate chirality on the system beyond their concentration. Okay, that's known and it's not surprising. But then Bert group, they sent us from each of these samples, they sent to us and asked us to do the spin polarization measurement of this. And when we do it, we get these results. So you see here, it's amazing. Our spin polarization results really follow the CD intensity. This effect was observed later by many groups, and we know now that actually the spin polarization in the CISS effect is proportional to the asymmetric factor, or if you wish, with the magnetic transition dipole moment in the case of the circular dichroism spectrum. So we know exactly how to relate the CD spectrum to CISS. Now, why it's so surprising? It's surprising because the CD spectrum is not a local property. It's not part of the molecule. It's all the molecule shows this, is responsible for the spectrum. It indicates that actually the CISS, the spin polarization of the electron going to the system, is sensitive to the polarizability of the whole molecule. And that's very important to appreciate. It's not a local property of an atom or electron colliding with one or two atoms. The electron going through feels the total polarizability of the system. Okay, now we go to another aspect of the CISS effect, which is also very surprising. We can absorb, of course, chiral molecules on a surface, and specifically, we absorb it on whole device. Now, for those of you that are not, despite the fact that most of you are physicists and probably know what is whole device, what is interesting here, so we have a gallium nitride, aluminum gallium nitride material with 2d electron gas of electrons, and what we have, 2 electrodes here, current is flowing here, and typically in such a device, we apply magnetic field perpendicular to this device, and we get potential, electric potential, perpendicular to the current and to the magnetic field, and that's called the Hall potential. In our case, what we do, we don't use any magnetic field, but we absorb chiral molecules here. On top of the chiral molecules, there is an electrode gate. The electrode doesn't touch the molecule, so there is no current flowing between this electrode and the device, but field is applied. So we apply only electric field. What the electric field does, it polarizes the molecule. So that's what we see. We see in this case, it's a L enantiomer, and left-handed enantiomer. You see the Hall potential as a function of the voltage on the gate. If it's D, you see the Hall potential as a function of the gate. So you see that you have L and D with opposite slopes. What it really indicates that in L, one spin is injected into the system, while in D, it's the opposite spin. And what we believe happening here, the electrodes here are looking like they are touching, but they are actually insulated from the molecules. And so what we have here, we inject spin from the molecule into the gallium arsenide or gallium nitride, depends on the system. And as a result, of interaction with the 2D electron gas, it stabilizes the electron here, and we see what is known as anomalous Hall effect. We proved that it's really anomalous Hall effect. So it's really interesting that by applying voltage on the molecule, we can inject spin. So what's going on here? So think about a molecule, chiral molecule, it's a singlet. But now we apply voltage. What happens when we apply voltage? One electron is transferred from here to here, or part of an electron. Doesn't have to be a full electron. But because of this transfer is spin dependent, we get here some spin polarization and here the opposite spin polarization. So please realize that the whole molecule is still a singlet. The total spin is 0. But at one pole, we have one spin. In the other pole, we have the opposite spin. If we take the opposite enantiomer, then the opposite spins are associated with the same electric poles. Now, why it's so interesting? Because singlet, as you know, is an entangled state. Namely, you cannot, in typical molecule, if the molecule is not chiral, by applying field, you cannot know if the electron that arrives here is one spin or the opposite spin, because it's superposition of the two spins because they are entangled. What we see in the chiral system, that the spins, because of the electron moving through chiral system, it's like measuring the spin, and therefore we break the entanglement, and we can know now, as we show with the whole device, which spin is here and which spin is here. That's really interesting. There are recent experiments by Mike Vasilevsky that he saw this breaking of the entanglement in EPR spectroscopy. Another thing that I'm not going to show results here, but we have it, is that the spins in this case are strongly coupled to the molecular frame. So when the molecules are tilted, the spin tilt with them. So the spin is aligned relative to the molecular frame. Now, why it's important? Think about interaction between two chiral molecules. When we have two chiral molecules, then when they interact, we get induced dipole interaction. And now, because as I said, if we have dipole, we have spin associated with it. So if these two molecules have the same chirality, then the interaction is through a singlet potential, while if they are opposite chirality, we have here interaction on a triplet surface. So this will be a interaction that is allowed. Here there is a repulsion. What this means that the interaction of chiral systems does not only depends on their conformation or structure, it depends also on electronic properties, namely on the spin exchange interaction between them. And that's despite the fact that the two molecules are singlet. The polarization of the molecule, one by the other, result in spin polarization, local spin polarization at the electric poles that results in different interaction between in the case of two enantiomers that are the same versus two enantiomers that are different. I will go quickly now on the issue of what happened with the chiral molecules going to interact with ferromagnet. That's work that was done in collaboration with Yossi Paltiel group. And what you see here, there is a ferromagnet on top of which chiral molecules were absorbed. And what you see here is simply the topography done by AFM, and you see these squares. And now, instead of topography, we can use magnetic AFM that measures the magnetic field at these squares. And what we find now, that in one case, the magnet of the ferromagnet underneath these molecules is pointing up. In the other case, it's pointing down. So how it happens? Again, it has to do with the spin polarization of the molecule. When the molecule gets to the surface, it charge polarizes. As a result, there is a spin polarization. It can bind to the surface efficiently if the two spins here are opposite. And so it's worth, in terms of free energy, for the system to flip the spins of the ferromagnet so it will be anti-parallel to the spin of this electron. So we see how adsorption of chiral molecules can control the magnetic field of a weak ferromagnet. I don't have much time, therefore I will skip something, and because I want to tell you something really new that I think you are the first to hear about it. And you know, typically when we have two enantiomers, we believe, and it's written in textbook, that the physical and chemical properties of two enantiomers are identical. However, when we did many of the CISS experiments, we found that we don't get this effect. In many cases, and here is summary, I'm not going to go in details about them, we find difference between the two enantiomers. And in the beginning, I thought that it has to do with purity of the samples, and I even wrote it. But with time, we got more and more molecules that were made in the same way, and the two enantiomers were purified in the same way, and still the results were not the same. And it was very surprising. Till we started to think about it. So I want to show you an example of this. Here it's a case with work that we did in collaboration with Frank Glorious from Münster, and they synthesized these molecules. It's completely static molecules, and it's carbon, it binds to the surface, and the two enantiomer. And we measure with these molecules when we coat electrode in electrochemical cell and study oxygen reduction. What we see that when the molecules are namely there are two asymmetric carbon there. So at RR we get this efficiency. When it's SS, we get this efficiency in the electrochemical cell, namely, as you see, different potential for the reaction. If we mix them, then we get the average. And whatever we did, we could not explain it. And now I want to show you what we think is going on here. The spin-orbit coupling in chiral system can be in an artificial way divided into two elements. One is the atomic spin-orbit coupling of the atoms, and another one is the topological one, namely the curvature of the potential, of the chiral potential, contribute to spin-orbit coupling, and this curvature can be, of course, one way or different way for the two of the two enantiomer. Now, the spin-orbit coupling, you have to appreciate, for electron going through the system, it has two components. It has the real part that we all know, but it has a phase, imaginary part. Now, for the atom, when electron moving near atom, there is a phase, We know it, it's an imaginary part. And it's the same for atom. Doesn't matter if the atom is in one enantiomer or another enantiomer. However, for the curvature, the phase is different if we have one enantiomer or the other opposite enantiomer. As a result, what we get that although the real part of the spin-orbit coupling is the same for both enantiomers, the imaginary part is different. Now, what it means that the imaginary part is different? It means that the orientation of the J vector, namely the total angular momentum vector for electron going through the system, is different for relative to, when I speak orientation, I mean orientation relative to the molecular frame is different for the two enantiomers. So you should realize the real part of the spin-orbit coupling is the same. And therefore, if you do spectroscopy, you will get the same J and so on. The energy level will be the same, identical. But for moving electron through the system, the effective magnetic field that this electron will feel will be different. So here's the story. Basically, think about it. We have electron moving, let's call it on this path. We will call it a Z. The total vector is either this or this, and you see the projection of this vector on the Z will be very different. Because it will be very different, the effective magnetic field that the electron feels, it will be different. This will result in different spin polarization for the two enantiomers. To summarize it, for electron moving through enantiomer, the spin polarization depends on the projection of the S vector, the total spin vector, on its path. And since the projection on the path will be different for the two enantiomers, we are going to get different spin polarization for the two enantiomers. Interestingly, this can be calculated ab initio, and it was done by the group of Anna Kirilov, and they indeed see in this system that the spin vector has different direction for the two enantiomers. And that was done in many systems now. By now, they calculated 3 or 4 systems. So since any interaction of molecules, chiral molecules, involve charge reorganization, any molecule involves charge reorganization, the charge reorganization in chiral system is spin dependent. Therefore, it is possible that two enantiomers will interact differently. What I mean by interact differently, because many interactions are spin dependent. For example, I showed you the interaction between two identical enantiomers depends on the spin exchange interaction. Therefore, spin exchange interaction depends how much spin polarization exists. Therefore, we expect to have different type of interaction, different strength of interaction for the two enantiomers. I will not elaborate on it, but this may be part of the explanation for homochirality in nature, because the difference here can be huge. Okay, I will summarize my talk and mention several things. First of all, spin enables long-range electron transfer, which is essential for biology. You have to remember that in biology, what is important is not the amount of current, because, for example, through protein, the transfer electron, typically only 500 electrons are transferred per second. So it's very low current. But what is important for biology, that the electrons that start to move will get to the end. If not, if we get stuck, it will destroy the protein. So the transfer should be with high yield, very high yield. You don't need high current. That's the reason I believe that nature picked proteins for electron transfer and not conjugated molecule as one would expect if we based everything about the physics of conduction. Second thing, polarizability must be considered as a very important thing. I didn't elaborate on it, but when electron is colliding with atoms through the current molecules, it polarizes the system. The polarized system is much larger spin-orbit coupling than the spin-orbit coupling of a closed shell atom. Therefore, we get enhancement of the spin-orbit coupling. This, I believe, is the reason why in CISS we see much larger spin-orbit coupling than one expects based on spectroscopy. In general, it's true that for electron colliding with the system, the spin-orbit coupling is not the same as as one gets from spectroscopy. When we measure, basically we are sensitive in spectroscopy to the field of the atom near the outermost shell. Now, angular momentum consideration must be included, especially when we speak about interaction between electron and phonon. What it means that the spin will be in Chiral system will be coupled to Chiral vibration or Chiral phonons, and they will be part of the conduction of the spin polarized electron. And that's what's observed experimentally now by several groups. Finally, the model for the mechanism of the CISS effect required to go beyond the Born-Oppenheimer approximation because of the essential role of vibration and phonons. It's also important that because of the polarizability, we must include also many electrons effect. I think these two elements are essential to understand correctly the CISS effect. These are the people in my group that did the work. Those with the red ring were involved in the works that I described to you, and thank you very much.
Thank you very much, Ron. That's always a nice talk. So I will have some questions later, but maybe we start. So whoever wants to have a question, please raise your hand, and I will promote you or write it down if you cannot share with or ask directly. Please go ahead and okay, let's see, allow talk. Sitze, Tyrion, can you maybe ask a question?
Yeah, thank you very much. Can you hear me?
Yeah, we can hear you well.
Yeah, super. Thank you very much, Ron. Sitze from the University of Groningen. So, yeah, you basically in the first part already described the experiments where you use conductive AFM to measure, well, with a magnet, a chiral molecule, right? You call it the spin polarization, but well, I think that we had already some discussion that this can also be described as magnetoresistance. And the main question I have based on your talk now from what you showed us, do we now fully understand, in your opinion, what is happening with this magnetoresistance? Because, of course, we have a description which, well, which could also be used to explain it, but or at least to point towards other directions. Can you comment?
Yeah, I think we understand what's going on here. I would say it's very short. First of all, when we put molecules, chiral molecules between two electrodes, and now we start to apply voltage, there is a as a result of the voltage, there is a polarization of the molecule. The polarization of the molecule is spin dependent. As a result, we get at the interfaces, we get spin barriers for electron conduction. And these spin barriers, they do two things. First of all, they enhance the spin polarization. That's why we can get spin polarization, which is higher than the polarization of the ferromagnet subset, for example, because we have an additional barrier on top of it. It makes the conduction non-linear, and as it was clearly seen, and by the way, that's important to appreciate, the conduction, I believe, all the experiments, including those that show straight lines when there is straight lines, they don't go to zero if you go with the voltage to zero. And therefore, I think in all cases, there is, if you wish, non-linear effect that results in polarization of the molecule. That's one important thing. The second important thing is that when electron is going through the system, the electron, because of simple electrostatic consideration, when you put electron in a system with relatively low dielectric, the field is huge. And the field results in polarization of the molecule. So the right picture to think about electron going through Chiral molecule is actually something very similar to polaron. And as a result, this polaron behavior enhances the spin-orbit coupling. It can be calculated and can be seen. Actually, it's interesting to realize that there are cases in Rashba scattering, in Rashba experiment, that where the spin-orbit coupling is by orders of magnitude larger than the spin-orbit coupling of the atoms involved. So I think we have something like this also in the CISS effect. So I think we do understand. By the way, if you take this model, and it was done, you get also, of course, breaking of time reversal symmetry. Time reversal symmetry doesn't play any role here, and because of two reasons. First of all, because of dissipation, the interaction with the phonon, and second, and that's very, very important, and because of the polarizability that creates different potential for electron going in one direction and electron going to the opposite direction.
I think the most important thing is the magnitude, not the symmetry. Let's move on to the next question.
One very short follow-up, because you mentioned also that.
What was your comment?
Go ahead. I mean, some of these things that you're describing that are quite natural from a symmetry point of view, that you understand that this will be affecting the physics. At the end of the day, the key thing that is to us always the puzzle is the magnitudes. Can we theoretically understand those magnitudes that are so much larger?
Okay, so I will answer directly. It's really interesting. In this case, you can do simple simulation calculation. They give you the order of magnitude. The truth is that there is no way available now to do ab initio calculation with this effect.
Okay.
Sorry, a very short follow-up on what you were just saying, because I think that a very crucial element is also, if we look at all these experiments, that even if you look at the resistance around zero bias, you have a difference in resistance, right? So this magnetoresistance, let's say the CISS magnetoresistance, is persistent in the linear response. And this has, of course, been a big part of the discussion.
I don't want to go to this discussion right now, but there is, I don't think that this effect is a linear response. Very clearly, it's not a real response, and we know, by the way, that you may get straight line even if there is no linear response.
Yeah,
But that's another.
sorry. I would like to interrupt here because there are very beautiful experiments which show that there is still a magnetoresistance in linear response. And if there is a linear dependence of the current on the voltage, it is linear response. I don't see any way how you can get around it.
Okay, if you look on this experiment for Florida, I assume that you refer to, in the experiment in Florida, if you check, the curve doesn't intersect zero. Does not intersect zero.
That is strange, right?
And that's strange, yeah. So that's definitely not a linear response.
Okay.
Okay, let's ask first Gernot. I think you were first, and then we let Bart ask away. Yeah.
Okay, Ron, I wanted to know about the topological part of the spin-orbit coupling due to chirality. Is this what you just before mentioned, the spin dependence of polarizability, or is it something else?
No. The spin-orbit coupling, I will make it very simple. Think about two p orbitals. If you have a curvature, the two p orbitals will start to overlap. This will give you an additional contribution to the spin-orbit coupling that does not exist in each of the atoms.
Mm-hmm.
And that's what I mean.
Okay, well.
So there is the field, basically, also in the calculation,
yeah.
and also in the theory, the field, as you can see that the field that you describe, the atomic field by themselves, they are not the full story in the case of spin-orbit coupling. The shape of the molecule, in a sense, it was discovered quite long ago for the carbon nanotube.
Yeah.
In carbon nanotube, they are relatively big and so on. The curvature is relatively small compared to molecules, but there already people saw that there is additional contribution to the spin-orbit coupling beyond the atomic spin-orbit coupling. And it comes because the atomic orbitals start to overlap.
Okay. Well, thanks.
One second, somebody's
Je suis là, Thomas.
Okay. Let's see. So, Bart, can you please go ahead and...
I'm sorry, I don't want to prolong the discussion too far. And Ron, you know that we think that CISS is a beautiful effect, but as a matter of fact, it can have many manifestations. And we have been trying in the past years to connect the CISS magnetoresistance to what we know from spin transport in microscopic systems. And to be honest, in our opinion, there still is a puzzle, an enigma. So that is what I would like to say.
No, but okay, only a comment. One has to be careful. First of all, when one try to compare to electron transfer in microscopic system, one has to take into account the fact that the path is not a straight path. That's very important. And the electron can be described as wave packet, and this wave packet interacts with the system. And that's something that, as far as I know, was not considered typically in the case of conduction in microscopic system. Now, the only way that physicists typically take the curvature into account is by Berry phase. And in molecules, typically it's not done. And Berry phase, in the case of room temperature, involve, of course, polarizability or dielectric constant, if you wish, and the dielectric constant at room temperature of this molecule as imaginary part, which is also very important, which is never taken into account if you do experiment at 300 millikelvin.
Okay.
And this cannot be ignored.
Okay, so I agree with you that the nature of the transport in these molecular systems is different. I fully agree with you, but then I think still it is a challenge, a puzzle, to now explain why now these systems behave so differently from what we are used to let's say conventional ferromagnetic systems. So,
but I think I say it for the large audience here. I think it's really important to appreciate that typically electron transfer, both in molecules and in mesoscopic systems in physics, was done within Born-Oppenheimer framework, typically even single electron case in many cases, and very typically didn't include any interaction like polaronic interaction with the system. While it's really interesting that in organic electronics, everybody speaks about polarons, of course. But somehow when you go to single molecules, people forgot about it.
Yeah, but typically the polarons are not so connected to the spin. That's the whole point, I think.
Right.
But in this case, you're claiming that the chirality of the systems in such enclosed confined systems, that chirality enhances the spin polarizability.
Right.
Okay.
Yeah.
I think that's what.
But because of
point is.
polarizability, because of if only to make it clear, if you want to think about it in a formal way, if you take the electric field in the spin orbit coupling and you develop it in the vibration coordinates, what you get, the first term involves, of course, contribution from vibration and includes spin exchange interaction, which is very interesting. So I will leave it here, but the point I make about it, I think it's really important that that's something that people will start to appreciate, that the reason it's so difficult to understand CISS effect is because it's really different sort of conduction compared to a linear path of an electron through a system at 300 millikelvin.
All right, let's move on to Jean-Philippe. Maybe you can unmute yourself and ask your question. Yeah.
Thank you, Rahul. Thank you, Ron, for the talk. In your conclusion, you mentioned that electron collisions electrically polarize the system, and that leads to an enhancement of the spin orbit coupling.
Yeah.
Now, these molecules, some of these molecules, but not all of them, have an electric dipole moment.
Right.
So, are you saying that the effect of collisions is larger than the intrinsic dipole moment of some of these molecules?
Yeah.
It is.
It's much more local.
Yes, local.
It's more local. So the simple picture, if you wish, is think about zero order approximation. Think about electron colliding with an atom that has a polarizability equivalent to the polarizability of the molecule. What you will find that the electron repel at least one electron away from the carbon. So the electron penetrate in the case of carbon, almost to the 1s shell. So the field that this electron feels is much larger than the one that we usually use for calculating spin-orbit coupling.
Okay.
But then
The point I retain is it's very local. Yeah.
So this is actually one question that I was...
No. It's very interesting here. The interaction of the electron is local, but the polarizability that plays the role here is a global probability of the property of the molecule.
Yes.
That's why.
Yeah, that's clear.
That's why the CISS is proportional to the optical activity. Both of them are sensitive to the anisotropic polarizability of the molecule.
Yeah.
Thank you.
So maybe just the last follow-up, and then we'll close the day for the day. So in this particular sense, it's clear that you're saying, okay, look, here you have to have molecular. We have some possible overlap between the different, as the chirality comes, the different orbitals, perhaps, of the molecule. But then, correct me, but I thought there was also some experiments in similar effects, but I don't know if it was weaker or lower in larger systems like DNA molecules or something, where definitely the scales are gigantic compared to the molecular ones.
No.
Am I false in that statement, or?
No. Okay, but we have to be careful here. That, of course, the length, we have crystals. We see the CISS effect in crystals that of micron length. But that's not the issue. The issue, what is the interaction? So the DNA, the scale of the interaction is still on the angstrom scale. I mean, the electron is interacting with the atoms on the angstrom scale.
I understand, but we do understand that. We of course, exchange interactions are complex, but some of them we can characterize them pretty well. I just see that if it is connected to that curvature, to that polarionic, there should be more of a. I would still like to see a direct test where you can actually get rid of it somehow by unfolding, in a sense, that chirality systematically.
Oh, okay.
That would be the way that I would understand it better, because right now I think the puzzle with Bart remains that there's still very large effects, and then there's still there are hints to where we go, what we're trying to understand it. Of course, it's a real beautiful effect. There's no doubt about it. But there's still a way to, which is great, which is the point of keeping us busy. But yeah, some of the things that you're saying about the topology, I would not call that overlap of the P waves topological in that sense. Yeah.
I will make it briefly. The polarizability in chiral molecule is spin dependent. That's the issue that you're missing here.
Yeah.
So even if an electron collides with an atom and charge is repelled from this atom, the charge that is repelled, another electron or part of an electron repelled from the atom, repelled in a spin selective way. And that's what makes the effect so special.
Yeah. I think that was clear that you're saying that chirality is enhancing the effect that you would expect for a single atom, that it's been enhanced once you start the polarizability.
Yeah.
Once you induce the polarizability, there is a clear enhancement that you wouldn't expect just without an inducing the polarizability. Yeah, some sort of resonant behavior.
Okay.
Okay, perfect. Okay, yeah, this is of course, as you guys can see, a very hot topic. It has been now for the last decade, but I think it's exciting, and as everybody comes from different directions, I think there will be more understanding. I want to thank all 90 of you that were watching live, 60 or 70 that we were here in Zoom, and the 30 in the line in the system. I would think I'll stop now the streaming now. And thank you, Ron, once again
Thank
for
you.
your talks. Are always fun to listen to. And